Now I will show you how a flyback converter works and how you'll find the ratio between VO and VD. So what you need to think about is when the switch is on and off. When it's on, the current will go through the transformer like this. This here, the mutual inductance, is a part of the transformer, and it will induce a current going through the diode here and through the resistor. Because we have a dot here and dot here, the current will go through down here and then up here. When this switch is off, there will go no current through the transformer like this. The current will instead continue going through the magnetization and go like this, which means that the current here will like to go here, but it can't because the diode here would be reverse biased. So there would go no current from this side to this side. All of the current going through the resistor comes from the DC link here. So the voltage of an inductor with a core is equal to the number of windings multiplied by the change of flux over the change of time. The V1 corresponding to N1 is equal to the change of flux when it's on over time. So this is the case when it's on. And when it's off, the V2 would be equal to N2 multiplied by the change of flux when it's off over time. In steady state, the change of flux when it's on should be equal to the change of flux when it's off. Forgot to mention that when the switch is on, V1 is equal to VD, because there would just be a wire here. So this point here will be equal to this point here. And when it's off, this VO here would be equal to V2. So V2 is equal to VO. Now if we solve this one equation here for the change of flux when it's on, and this equation for the change of flux when it's off, we can put those two fluxes into this equation and get the ratio between VO and VD, assuming that we also use these two. If we just solve this one here, so we can just solve the general one first. So the change of flux is equal to V over N multiplied by the change of time. So for the change of flux when it's on, this will be equal to V1 over N1 multiplied by T when it's on. And for the change of flux when it's off, it will be kind of the same. So V2 over N2 multiplied by the change of time when it's off. So if we put those two equal to each other, we will get V1 over N1. And this time here is equal to dt. So I can put that on this side. dt is equal to dt, where t is the period and d is the duty cycle. So this will be dt. Now we have the other side, so v2 over n2. And the change of time when it's off is equal to 1 minus dt. So put that in, 1 minus dt. Yes, so this one here is equal to VD, and this one here is equal to VO. So if we solve for VO over VD, we can just move this one over to this side here and move everything here over to the other side, right? And the first thing that we can see is that the t here, these two t's, cancel each other. So this will be equal to N2 over N1 multiplied by D over 1 minus D. So now I will show you the other method, and that uses the power balance. So the power coming out of the source should be equal to the power going through the output. So the power on the left hand side, so we can say that is P in. So if we want to find the ID, we need to look at the magnetizing current. So actually, when this switch is on, the current would only go through the mutual inductance and magnetizing the core, which means that there will go no current through here. So when it's on, ID is equal to IM. And when the switch here is off, there will go no current from here to here, which means that ID would be 0. So if we try to draw the graph here, try to plot the current. So let's say that this is IM peak, this level here. So ID will start rising until it reaches IM peak, and then it will fall like this and be 0 for a period of time, and then it would start rising again and fall. So this is a period, right? So this would mean that the average current going over here, it would be here. This would be ID average, so AVG. So the power going into the converter would not be constant, and therefore we need to find the average value to compare it to the power going out of the converter. So if we find the average converter going in, we can use that to find the average power going in. So what we want to do is just to find the area under this triangle here and divide it by the time, the period. I average would be equal to the peak current for the magnetization current divided by 2 because it's a triangle, and then we need to multiply by the time, when it's on, and then divide by the period. So that would be the area under this triangle here divided by the time it takes. So now we need to find this peak current here. We know that the voltage over here should be equal to VD. So the voltage here, it should be the same as here, right? So therefore we can calculate the current going through this inductor. Therefore VD should be equal to the mutual inductance multiplied by the change of current going through the mutual inductance here over the change of time when it's on. We know that the magnetizing current, the change of magnetizing current should be equal to the peak magnetizing current because it goes from 0 to the peak. And therefore we can solve this equation here for the magnetizing current, which should be equal to VD multiplied by the change of time over LM. And now we can put this into the equation for the average current. The average current is equal to, so it should be the peak value of the magnetization current, which is equal to VD multiplied by the change of time when it's on over the mutual inductance. And then we also need to divide by 2, so we put that in front here. And then we need to multiply by the T on here over T. We can simplify this further because T on is dt. So therefore we have VD multiplied by dt divided by 2LM. And here the T will go with the T, so we just have D. And now we can put this into the equation for the power here. And we will get that, so the P in, so it will be VD squared multiplied by D squared, multiplied by the period, divided by 2, and the mutual inductance. And this should be equal to the PO, which is VO squared over R. So now we need to solve for VO over VD. So we can just solve for the squared case first. So we can move this VD over and this R over, and that would solve it. So it's R multiplied by D squared multiplied by the time divided by 2LM. And now we can just take the square root of that. So this should be the other voltage ratio.